In a deficiency of B12, RBC remains big and it causes megaloblastic anemia. This megaloblastic anemia of vitamin B12 deficiency is actually a facultative function of vitamin B12 that converts folate into an active form of folate, which is needed for efficient DNA production. So, treating vitamin B12 deficiency with folate may correct this disorder of cell maturation, but it will mask the other disorders of vitamin B12 deficiency. This is the big RBC macro. This occurs in vitamin B12 deficiency, folate deficiency, and a chemotherapy with methotrexate. Methotrexate is a folate antagonist. The normal RBC is a biconcave. This is a best shape that suits well to pass through a single file in the capillaries. The one less red color in them are hypochromic, and that occurs in iron deficiency anemia, thalassemia, sickle cell anemia. This is a sickle shaped RBC, and in microangiopathic pattern of hemolytic anemia. And this is the round RBC, hereditary spherocytosis, and this is a leptocyte that occur in hereditary leptocytosis, and this big RBC that occurs in megaloblastic anemia. So what happens in vitamin B12 deficiency, that this 5-methyl tetrahydrofolate is converted to tetrahydrofolate. This is the active form which is required for cell maturation. Remember, this 5-methyl tetrahydrofolate is not the active form. It is the tetrahydrofolate which is the active form. And also this homocysteine here requires conversion to methionine. The enzyme is methionine synthase that requires vitamin B12. And then this methionine is converted to S-adenosyl methionine, S-adenosyl homocysteine, and back to homocysteine. So in a deficiency of vitamin B12, excess of homocysteine is found that causes homocystinuria, and this homocysteine is converted to cysteine, and this requires vitamin B. So here these are the different reactions again, that tetrahydrofolate to active form, methyl tetrahydrofolate to active form of tetrahydrofolate, and B12 converting homocysteine to methionine. This is homocysteine to S-adenosyl homocysteine and then to S-adenosyl by methyl transferase. The other action of vitamin B12 is the conversion of methylmalonic acid or methylmalonyl-CoA to succinyl-CoA. Deficiency of vitamin B12 causes defective myeloid. So all these odd chain fatty acids from acetyl-CoA and from cholesterol and also from methionine, threonine, isoleucine, and they are converted to propionyl-CoA, which is a 3-carbon atom, takes a carbon, an ATP, converts it into methylmalonyl-CoA. Biotin is a cofactor. And then methylmalonyl-CoA is converted to succinyl-CoA by the enzyme methylmalonyl-CoA mutase. And this is the step where this enzyme requires vitamin B12 for the conversion of methylmalonyl-CoA to succinyl-CoA. Deficiency of vitamin B12 prevents the conversion of methylmalonyl-CoA to succinyl-CoA, leads to excess of methylmalonyl-CoA or methylmalonyl aciduria. So this is the other picture. Valine, isoleucine, methionine, threonine, and odd chain fatty acids are converted to propionyl-CoA, and then biotin required for the conversion of this propionyl-CoA methylmalonyl-CoA, and that requires B12 for conversion to succinyl-CoA to join the TCA cycle. Here is methylmalonyl-CoA, propionyl-CoA, methylmalonyl-CoA converted to succinyl-CoA to join the TCA cycle, and a deficiency leads to excess methylmalonyl-CoA that leads to methylmalonyl aciduria. In the metabolism of homocysteine, see that if homocystinuria and there is B6 pyridoxine is required here, at 2 steps to convert homocysteine to cysteine requires vitamin B12 to convert homocysteine to methionine. B12 deficiency is associated with an increase in propionic acid and methylmalonic acid. The activities of fatty acid synthetases and acetyl-CoA carboxylase is 2 to 5 folds increased in vitamin B12 deprivation. Methylmalonyl-CoA inhibits the synthetase activity and it is a myelin destabilizer. Excessive methylmalonyl-CoA prevents normal fatty acid synthesis. If this abnormal fatty acid is incorporated into myelin, resulting myelin will be too fragile and demyelination will occur. Vitamin B12 is required for the production of methionine, a precursor of SAM, adenosylmethionine, which is required for methylation reaction. These reactions are essential for myelin maintenance. If myelin sheath is damaged, it causes disruption in the nerve impulse transmission. Homocystinuria may cause damage to arteries and clotting and may cause strokes and heart attack. Myelin damage results from B12 deficiency in the presence of adequate folate. Methionine is more specifically a vitamin B12 deficiency problem. Methionine is in turn necessary for methylation of myelin sheath phospholipids. B12 deficiency causes neuropathies even if folic acid is present in good supply, but anemia is not present.